Good morning, everyone. It is my honor to be presenting here today. And my name is Ali. I'm a PhD student and graduate research assistant at the University of Kansas. And today I'm going to talk about the anchorage of large, high-strength headed reinforcing bars. So first, I will give an introduction and I will talk about the problem statement. Then I will talk about the KU studies and findings on the subject. Then I will talk about the current project that is going on. And at the end, I will talk about the future research. So first, we can talk about what are headed bars and why we need them. So as we know about the development length, it is the minimum required length for the bar to be able to transfer the stresses without the bar slip. So we need to provide that minimum length of embedment. Sometimes, as shown here, the geometry of our member doesn't allow us to provide that minimum development length. So a solution in such cases is using what are called hooked bars, that they have a tail or bend at the end of the bar. And the bend can be 90 degrees and 180 degrees with the requirements shown here. So for the hooked bars, the development length is defined from the back of the tail to the front face of the column in a beam column joint. And here we have the effective depth of the beam. So the ratio of the effective to development length is an important factor when it comes to anchorage strength. So hook bars are good, but there could be problems. As you can see here, especially when we are using larger diameter hook bars, we can have the problem of congestion in the joint region. And that can be very bad in terms of constructability. So to solve this problem, we can use what is called headed bars. So in headed bars, we eliminate the tail of the hook, and instead we attach a head to the end of the bar. And heads can have different shapes, but the important factor is not the shape of the bar, it's the ratio of the area of the head to the area of the bar. So for the headed bars, the development length is defined from the bearing face of the head to the front face of the column. And again, same as hooked bars, the ratio of the effective to development length is an important factor. So we can talk about how the bond mechanism of hooked bars and headed bars. So for the hooked bars, they gain the anchorage strength by having these bond stresses that are acting along the deformed shape of the bar and the normal stresses acting on the tail of the hook. Whereas for headed bars, we have the bond stresses, same as hook bars, but instead of normal stresses, we have the bearing forces on the head. So you can see that that's why the ratio of bearing area of the head to the area of the bar is an important factor. So this picture shows a typical headed bar that we use. This is called the swage length. And here we have the bearing face of the head. So in the previous version of the ACI 318 code, ACI 318.14, there were conservative limits on the use of hooked and headed bars, mainly due to the lack of experimental data. So for the hooked bars, the limits were 80 kSi for the bar stress and 10 kSi for the concrete strength. And for headed bars, the limits were even more conservative, 60 kSi for bar stress or steel tensile stress, and 6 kSi for F'(C) or concrete strength. So this means that we couldn't take advantage of using a higher strength concrete and steel. So these were the main motivations for a comprehensive study that started here at KU, with the goals of expanding the understanding of the anchorage behavior and developing new design provisions for hooked and headed bars. So from 2002 to 2016, they tested 300 hooked bar and 202 headed bars specimens. And the type of specimens, we call them simulated beam column joints. It means that we construct the column, we make the column, but we simulate the beam. We represent the behavior of the beam with the hooked bar or headed bar. So here, the hooked or headed bar represents the top longitudinal reinforcement of that imaginary beam. And this bearing member with the compression force represents the compression zone of that virtual beam. So the major findings throughout those years was that hooked and headed bars behave a lot alike. And for the same embedment length, the headed bars are stronger. They found that those hooked and headed bars are weaker individually than widely spaced hooked and headed bars. They found that hooked bars with 90-degree and 180-degree bends have similar anchorage strengths. An important finding was that ACI through 1814 provisions overestimate the contribution of concrete strength to anchorage strength with using a square root of F prime C in the equation for calculating development length. And they found that it can be better represented by using F prime C to the quarter power instead of a square root. Also, they found that confining reinforcement increases the anchorage strength of hooked and headed bars. And at the end, they developed descriptive equations to calculate the anchorage strength of hooked and headed bars based on the tests on the number 5, number 8, and number 11 hooked and headed bars. So the findings led to modifications in the newer version of the code, ACI through 1819. And these are the new equations to calculate the development length of hooked and headed bars. And the reds are the changes. They introduced some factors to, for example, account for presence of confining reinforcement in the joint region. This factor psi sub c is interesting. So what happened is that they didn't change the square root of F prime C to the quarter power. Instead, this factor helps reducing the required development length for the F prime C values of less than 6,000 psi. And that means that this psi sub c factor approximates the quarter power. So even with those new modifications, there are still limits on the use of large diameter hooked and headed bars. For example, for headed bars, the maximum bar size allowed is number 11. And the main reason is that we have the lack of experimental data on number 14 and 18 bars. So that's the main motivation behind the current project. And our goal is to expand the available data on the anchorage strengths of number 14 and 18 bars and use the experimental results to propose design criteria for these large bar sizes. So talking about the specimen design, the same as the previous studies that I talked about, we are doing simulated beam column joints. And we designed the specimen so that the anchorage failure occurs in the joint region. And the key variables we are studying are embedment length, number and spacing of bars, widely and closely spaced, area of confining reinforcement in the joint region, bar size, concrete strength, 5 to 15 ksi, and the stress of the test bars up to 150 ksi, which means that we are considering the high strength concrete and steel. So this drawing shows the forces applied on the specimen from the reaction frame when we test them. So here we have the headed or hooked bar, and we are like pulling it out of the specimen. We are applying tension, and through this bearing plate, we apply the compression. So this is our joint region. This is the negative moment that we have in a beam column joint, and these forces are the shear forces that are present in a joint, like above and below the joint. This photo shows our complete test setup. So the columns, we cast them vertically, but for the test purposes, we lay them down horizontal on these two concrete blocks. And this is our reaction frame. And these are the same forces that I showed you in the previous slide. Joint region, this is the headed bar that you can see is sticking out of the column, and we apply the tension to it. And through these beams, we have the compression, and through this member, we have that upward force. So I can talk about the results obtained so far. So far, we have tested specimens with number 14 bars that have 2 bars spaced at 18 inches, which is considered widely spaced. And the concrete strength we have tested so far is 5 to 13 ksi, We had bar stresses up to 150 KSI, embedment length 22.7 to 35.8 inches, and we had confining reinforcement in the joint region. I mean, the specimens with and without confining reinforcement. So these are the headed bar specimens that were tested. Like a summary of the test results. So T over TH is a ratio of the Anchorage strength obtained in the test to the Anchorage strength calculated based on the descriptive equations that I talked about. So the coefficient of variation of descriptive equations are approximately 12%. So it means that this average of 0.97 is within that range. That means that the descriptive equations that were based on number 5, 8, and 11 bars are still working for number 14 bars so far. And for the hook bar specimens, same. We have an average T over TH of 1.06. Again, within the range of descriptive equations. So the typical failure mode that we observe in our test is that first we have this vertical crack due to the slip of the bar as we are pulling the bar out. Then the cracks start to propagate throughout the joint. These branch-like cracks, you can see here, they are developing and propagating. And also this vertical crack develops and moves toward the location of the head. And at the failure, this we call it a concrete breakout that has a cone-shaped failure surface. And you can see the headed bar here that is exposed. And this shows the front face of the column with the concrete breakout and the chunks of concrete blown away. In terms of the future steps of this ongoing research is that we want to finish the test on number 14 hooked and headed bars. We are moving forward now with closely spaced specimens, the specimen that has 3 headed or hooked bars, spaced at 6 inches, which is considered closely spaced. And then after those are done, we will move on with design and fabricating specimens with number 18 hooked and headed bar specimens. As a summary, I talked about the need for obtaining experimental data on large diameter hooked and headed bars. I talked about the current study that is going on the Anchorage strength of number 14 and 18 bars, and I showed that the results obtained so far match fairly close to the previous test. And I also talked about what is the future planned for the ongoing study. Thank you so much, and if you have any questions, I'm happy to answer.